Hello and greetings, everybody.
Hope you guys are doing all right this evening. Have you ever wondered how much the Earth is worth? Well, I'll tell you right now, it's anywhere between $4 and 17 gazudo dillions. 17 gazuru dillion dollars. Anywhere between this and this.
Why?
Well, that's
Oh,
that's a long that's a really long discussion. So we'll instead discuss something that's almost infinitely times easier to comprehend: the conservation of
linear momentum as well as impulse and its relation to elastic and inelastic collisions and kinetic energy.
stuff like that. Stuff like that. Okay, so let's start like this. What is momentum? Well, momentum, at least defined by a formula, is going to be denoted by a symbol p, which is a vector, is equal to some mass times some velocity, which is some vector. So if you have this mass and it's moving like this, and has this velocity and this mass, this thing has a momentum of mass times its velocity. That is going to be its momentum. Okay, cool. Now let's talk about something a little bit more important. We're going to talk about the change in momentum. What about change in momentum? Change in momentum. Change in momentum in this case, denoted by delta p, which is what this symbol is. It is not pyramid. It is delta. Delta p is equal to some mass times change in v. Well, it's equal to change in momentum. That's really it. But it can also be equal to. It could be equal to some force times some change in time. That could also be this right here, change in momentum. And the units for this is going to be Newton seconds, as well as this. This is also going to be Newton seconds. Okay, so let's see if we can apply that. So we have this ball again. It has mass m and velocity v, right? We apply a force. This has an initial momentum of its mass times its velocity, which I'm going to denote initial velocity. Its final momentum, after we apply some force, some force in this direction for change in t amount of time. So this could be 10 newtons for 3 seconds or something like that. Its final momentum is going to be its initial momentum plus the change in momentum that we applied, that is applied, which is going to be this right here, F times change in t. And these formulas are quite useful because you can then step away further from kinematic equations such as v squared, v final squared equals v initial squared plus 2ad. This is primitive stuff. This is caveman ooga booga stuff. We don't touch this stuff anymore, although we probably will in the future.
again.
But we could just use these formulas, or we can use our energy formulas to calculate how much something will change, given we have the right stuff to calculate it. So if we have mass, we have velocity, then we calculate momentum, and we have a force and a change in time. We can calculate how much how much faster that mass is going to move if we apply this force for a certain amount of time on that object. You can sort of imagine it like you're applying. You got it. Last example. You have a truck, right? You have a truck, and you apply some force on it. Well, let's say this truck is rolling downhill. Well, this is not very downhill. I don't think I can rotate. Can I rotate? No, I can't rotate. Oh gosh, dang it. No. Let me just draw it again. Okay, let's say this truck right here is rolling downhill, right? It's rolling downhill, and we desperately need to stop it. Actually, no. Let's just say it's rolling forwards for the sake of simplicity. It's rolling forwards with a velocity v, and it has a mass m, right? That means its momentum is going to be equal to mass times velocity, whatever that is going to be. And then we apply, and if this is us, we're sad because our truck is, we're going to have to stop the truck. And we're applying a constant force, F, and we apply it for, say, for a change in t amount of time. Let's say change in t could hypothetically be 3 seconds. It could be 4 seconds, and it could be maybe 10 years or something like that. Whatever amount of time you wish to use, that is change in time. So we apply that on there, and it's the final momentum of the car is going to be its initial momentum, which is mass times velocity, plus, well, in this case, because force opposes its initial velocity, it's going to cause it to decelerate. It makes sense for it to oppose its initial momentum. You're going to reduce its momentum. It's going to slow it down. So it's going to be minus force times change in time, right there. Okay, cool. So that's one thing right there. Another thing that we have to talk about is
Going to be, let me look at this real quick. One thing we're going to look at very soon
it's going to be collisions. This is where we use momentum the most. Say this car, it's going this way, right? And it runs into this car, which is going this way. After they hit and they collide, right? If they collide, there are two different kinds of collisions. They're going to be elastic, which I'll just elastic, and then inelastic.
Those are going to be the two kinds of collision that we can have.
The difference between these two is that, say this well, you probably won't see this in at this scale, but hypothetically speaking, if this ran into this one, right, and after they collided with each other, they started going in opposite directions. This is what we call an elastic collision. After they collided, they separated. Or this can be opposite directions. This can also be in the same direction if we wanted to. But the key concept is that they separated after the collision. Elastic collision, they separated. And under an elastic collision, two things happen. One, momentum is conserved. Momentum conserved. And let me move this here. Momentum is conserved, and kinetic energy conserved. In an elastic collision, two things stay constant: the momentum and the kinetic energy. In an inelastic collision, just the momentum stays constant. The kinetic energy does not. This does not stay constant. In an inelastic collision, after they collide, I'm going to write ELA, not English Learning Arts, but rather elastic. After they collide, in an inelastic collision, they stick together. You could often see this in actual car accidents. After two cars hit, they're stuck together, and what you will notice is that they lose a lot of their momentum. They slow down. They move together, but very slowly, and that's what happens. They lose some of the energy, and they lose some of their kinetic energy upon collision.
and only their momentum is conserved, but their kinetic energy is not. We will observe how to apply this soon. Okay,
So,
on to question number 1 of the review I created.
question 1 asks, question 1 gives 2 blocks. This block right here, which has a mass of m1 and a velocity of v1, and this block right here, which has a mass of m2 and a velocity of v2. What's the momentum of block 1? Well, let's see. Go ahead and try to recall the formulas for momentum. Well, we just need one, but try to recall as many of them as you can. It will help you with your memory. Okay, cool. I will assume you've taken the chance to go ahead and recall. So momentum is going to be equal to mass times velocity, both which is a vector. So the momentum of block 1 is going to be its mass times its velocity. So let's see. Its mass is 10 kilograms and its velocity is 15 meters per second. So the momentum for block 1, which I denote as P sub 1, is going to be equal to 10 kilograms times 15 meters per second, which is going to be equal to 150 Newton seconds. I may not have said this earlier, but this is one of the SI units for momentum, I believe. I don't think they have an actual name for it. For example, like force is newtons, work is joules, power is watts, but for momentum, it's just Newton seconds. Or you could do kilogram meters per second, I believe kilogram meters per second. That's also another way to write it, but you're going to see me write it this way. Okay, so P2 is going to be equal to 5 kilograms, 18 kilograms, 5 kilograms, 18 meters per second, times 18 meters per second. That's going to be equal to 90 Newton seconds. So now we have the momentum of block 1 and block 2. All right, question number 2. We have this cannon. We're just going to assume that this is a cannon. Poorly drawn perhaps, but a cannon nonetheless. So this cannon has a mass of 300 kilograms. No, this cannon and cannonball above have a mass of 300 kilograms. And the cannonball has a mass of 30 kilograms. The system is initially at rest. Then the cannon is fired, sending the cannonball flying at 117 meters per second. How much mass does the cannon, not including the cannonball, have? Go ahead and take a try at answering A, B, and C, and then resume. Yeah, you get the drill. Okay, so for this first part, the cannon and the cannonball have a mass of 300 kilograms. So that translates directly to M1 plus M2, which I will write like this. M1 stands for the cannon. M2 stands for the cannonball. It's going to be equal to 300 kilograms. M2 is going to be equal to 30 kilograms, which is the mass of the cannonball. So if we substitute for M2 here, M1 plus 30 kilograms is equal to 300 kilograms. So we subtract from both sides and we get M1 is equal to 270 kilograms. So that's the answer for A. Okay. That's the answer for A. How much how much momentum does the cannonball have after it's fired? Recall the formula for momentum is equal to P, which is a vector, mass times velocity, which is also a vector, and then that's going to be equal to the mass of the cannonball, M2, times the velocity of the cannonball, which I'll denote as V2, V sub 2. So M2 is going to be equal to 30 kilograms, and then V2 is going to be unknown. No, I lied. It is known. 117 meters per second. This is going to be equal to, I'm not doing this in my head, 3,510 Newton seconds. How fast does the cannon move? Okay, now this is an interesting question. Okay, so for this question, I'm going to give you an analogy. Let's imagine you are sitting on, let's say ice. Let's say you're sitting on ice. If you've ever stood on ice before, you're standing on ice. This is you, or this is me, or this is both of us. If we are, I don't freaking know. Anyways, we have this right here. We have this, and then we have some sort of, let's say, box. We have some sort of box, right? When we push this box this way, what happens to us? If you recall, I believe it's the Newton's third law, that states. Hold on, let me just make sure. Yes. Okay. For Newton's third law, every action has an opposite and equal action. So we apply this force on this way. We apply a force this way as well. So we could think of this in terms of momentum. This has a momentum of m1v1. Let's say hypothetically this has a mass of m, and its velocity is going to be 10. Right? What about us? We have a mass of m2. And our velocity is going to be negative because this plus this, this is going to be, our momentum is going to be equal and opposite of this thingamabobber's momentum. That's an observation of Newton's third law, right there. So how fast does the cannon move? You can write it down like this: P1 is equal to P2 in this case, because there's no external force applied. No external force is applied in this case. Everything that is acting on anything is part of the system. The cannon acts on the cannonball acts on the cannon, and that's all that's happening. We're not having the hand of God apply some arbitrary amount of force out of nowhere and stuff like that. So there is no change in momentum. P1 is equal to P2. Therefore, change in momentum is going to be equal to 0. So let's see. Let's go ahead and write down our momentum formula. So M1, which is going to be the mass of the cannon, times V initial. What's the initial velocity of the cannon? Is going to be 0. What about the cannonball? Mass 2, and then its velocity is 0. This is going to be equal to its final momentum. So let's start with the cannonball, which we know. Its momentum of the cannonball is going to be 3,510 Newton seconds, plus the momentum of the cannon, which is M1 times V1 final. I'll write it like that. We know what M1 is. M1 is going to be equal to 270 kilograms times V1 final. Okay, cool. So what do we know? This is going to be 0. So we just have one unknown in this equation, and we can solve for that. Oh, okay, so let's move things around. And what we get is 3,510 Newton seconds is equal to 270 kilograms times velocity 1 final. Oh dear, it's not supposed to look like that. So we divide both sides by 270. And what we get is V1 final is equal to 3,510 divided by 270. And what we get is that the final velocity of the cannon, well, hold on, wait, something's wrong here. Negative 3,510. I subtracted from both sides. That's going to be negative. So V1 final is going to be negative 13 meters per second. Now, does this make any sense? Oh, let's see. We have this massive cannon, right? This cannonball is fired out of it. So, kaboom, kablooey, this cannonball goes flying this way. And if you imagine, if you know anything about, say, firearms or artillery, this causes recoil. This causes the weapon, in our case, is going to be this cannon to fly backwards. Because momentum is conserved. So the next time you're playing any kind of first-person shooter or any kind of game with guns and you're experiencing recoil, you think to yourself, "Wow, this is amazing. This is extremely realistic." They are applying conservation of momentum in the guns. That is amazing. So, yeah. Okay, so a slingshot mounted to the ground shoots pebbles of mass 3 kilograms to a speed of 48 meters per second. If the slingshot applies a constant force of 800 newtons on the pebble, how quickly can it fire a pebble, and what is the impulse applied on the pebble? Okay, let's see. Okay, so there's something I didn't say bluntly. I didn't define impulse per se. Change in momentum basically is impulse. That's what impulse is. And if you recall, the formula for for change in momentum is going to be some force times change in time. That is all that impulse is. So with that now, we can put this over here. Cool. Okay, so this slingshot is mounted to the ground. So in other words, momentum in this case. Okay, let's continue. So it shoots a pebble of mass 3 kilograms to a speed of 48 meters per second. How quickly can it fire a pebble if it applies a constant force of 800 newtons? Okay, so let's see. We have mass and we have velocity. So we have momentum. Its initial momentum. Its momentum of the pebble after it's fired is going to be equal to 3 kilograms times 48 meters per second. Its mass times its velocity. This is a vector. So what else do we have here? Okay, so initially, let's imagine this. This is slingshot right here. This slingshot right here is like this. Right? This is the wooden part or steel part of the slingshot, and this is the string, right? And then it goes to a state like this. Something like that. It goes from charged up to here. Fun fact, this is a form of potential energy. You'll see it very soon, or you've already seen it. This is this isn't exactly a spring, but it can be seen as the potential energy stored in a spring, 1/2 kx squared, if you wish to write it like that. Not all potential energy is based off of distance from the ground. This is an example of that. Okay, so continuing, you can disregard that information if you want to. It may or may not be important, but if you like random information, yeah, write that down. Its momentum, we have it here. It goes from here, its initial momentum, pi, is going to be equal to, its velocity, its initial velocity is going to be equal to 0. So its initial momentum is going to be 3 kilograms times 0 meters per second, which is going to be 0 Newton seconds. Oh, I should probably calculate this. Its initial momentum is 0, and then its final momentum is going to be equal to this. P final is going to be equal to 144 Newton seconds. There is a change in momentum, and what is a change in momentum?
Change in momentum is going to be impulse, which is going to be definable by this formula right here. This is going to be equal to is change in momentum, which is going to be this. You can take the initial, you can take the final minus the initial, 144 minus 0. So change in momentum is going to be 144 Newton seconds, which is going to be equal to some force times some change in time. In this case, the impulse applied on the pebble. We have the force that is that this catapult, that this slingshot applies on the ball, on this pebble. It applies a constant force of 800 newtons. So 800 newtons times some change in time. So in other words, we applied a force over some amount of time to change the momentum of this pebble from 0 to 144 newtons per second. Newton seconds. That is basically what is going on here. So if we divide both sides by 800, we're able to solve for t. And t is going to be equal to is going to be equal to 0.18 seconds. So in other words, this is how much time it takes for the pebble to go from this to where it stops being in contact with this thing, to where it accelerates it up to this right here. This is how much time it takes. So what is the impulse applied on the pebble? Well, we have the formula for impulse, which is going to be 800 newtons times 0.18, which is going to be 144 Newton seconds. Cool? Cool. All right, so this is an interesting question. If you were in class, you would have seen this before, but if you haven't, no worries. I will show you how to do it. I'll show you how to do it. This is going to be, you may or may not see this on your homework or on the test, so it will probably help you to see this. Okay, so let's see. We have a force versus time graph. All right. Cool. Okay, so given the force versus time graph above, what is the total impulse? Well, let's go ahead and define impulse. Impulse is going to be changing. P is going to be, I usually don't write I, because that's going to be the symbol of something else very soon. You'll find out soon enough, but for right now, I'll just denote it as change in P. Change in P will be impulse. Going to be change in P is going to be impulse. Okay, so impulse, if you recall, is going to be force times change in time, or in this case is going to be a change in force times a change in time. It's a bit complicated, but we'll just go with this for right now. Okay, so what is the total impulse? So let's see, what do we do here? Well, you might just jump ahead and say you just calculate the area under this, but what is the area under this? Let's imagine it. So we have this. Let's say we have a rectangle that's this tall and this wide. This tall and this wide, right? What is the width? The width is going to be the 2 to 3 milliseconds. So that's going to be 1 millisecond. And then its height is going to be 1, 2, 3. It's going to be 3 newtons. So what we're doing here is multiplying force times time. In other words, that is going to be equal to impulse. This graph gives you force in relation to time, which is going to be change in change in momentum, which is impulse. So now you can go ahead and find the area underneath this, now that you have an understanding of why you're finding the area underneath this. So the total impulse, let's see. what I usually do is I break these up into shapes that can be easily calculated. Shapes that I know the formulas of are going to be a square, a circle. Well, let's hope we don't ever have to use a circle, but a square and a triangle are going to be most of the shapes you're going to see on a graph. So let's go from here. So we have this first part, which is going to be a width of 1 millisecond and a height of 3 milliseconds. Recall that the formula for a triangle, for the area of a triangle, is going to be equal to 1/2 base times height. So its base is going to be 1 millisecond. Its height is going to be 3 newtons. Divide that by 2. This is going to be equal to 1.5. 1.5. Well, this is milliseconds, so we're gonna have a bit of a problem there. If we want this in terms of impulse, true impulse, we need it in terms of Newton seconds. So a millisecond is going to be equal to one. There are 1,000 milliseconds in 1 second. So in other words, a millisecond is going to be 1,000th of a second. So this is going to be 1 over 1 over 1,000, 2 over 1,000, 3 over 1,000, and so on. So if we do 1 over 1,000 times 3, that's going to be 3 over 1,000, which is going to be 0.0015. I'm not going to write that though right now. Let's just, to keep it simple, I'll write it like this: 1.5 e negative 3 you know what, forget it, I'm going to add them all up right here. So we're gonna have this first part is going to be its base, which is 0.001 seconds, times 3 newtons, which is going to be and then everything divided by 2, which is going to be 0.0015 Newton seconds. That's what it's going to be equal to. This is going to be the area right here. That's one part. And then the second part is going to be 1 millisecond, 3. So that's just going to be 0.003 Newton seconds. And from here, I'm going to be more quiet and just calculate the rest. Okay, so this is going to be the total impulse of this graph. Okay, so if there was a force applied on a block of mass 30 grams, what is the total change in momentum? Okay, let's see. If the force was applied, what's the total change in momentum? Okay, so let's see. Change in momentum is going to be defined as change in force times change in time. But if you paid enough attention, you would have noticed that the change in momentum, what is that? Change in momentum is going to be impulse, right? If the change in momentum is just going to be impulse, which we've calculated already, which is going to be 0.0135 Newton seconds. Okay, so assuming the initial velocity of the ball of the block was 30 grams, what is the velocity and momentum of the block at t equals 6 milliseconds? So at t equals 6 milliseconds, it's basically done everything. So change in momentum is going to be that. So its initial, let's see. It's going to be the initial momentum of the block, and then it's going to, after we apply this change in impulse, change in momentum, my bad, this is going to be its final momentum. So its initial momentum is going to be equal to 30 grams times 0 meters per second, which is just going to be 0 Newton seconds. Okay, so we have 0 Newton seconds plus its change in momentum, which is going to be 0.0135 Newton seconds, and this is going to be equal to mass times change in velocity. Recall that impulse is also equal to this as well. So if we equate that to this, 30 grams, well, for 1,000 grams, there's 1 kilogram. So for 1 kilogram, for 1 gram, there's a thousandth of a kilogram. So we are going to divide this by 1,000, or what we're going to get is that the mass is going to be equal to 0.030 30 kilograms. Yeah. So 0.030 kilograms times some change in velocity. So we divide both sides by this.
What we get is change in velocity is going to be equal to 0.45 meters per second. Okay, next part. What is the velocity and momentum of the block at 7 milliseconds? Well, it's right here. There's no other forces applying, so the change in momentum is still the same. So in other words, it's still going from 0 Newton seconds of momentum to 0.0135 Newton seconds of momentum. So its final velocity is still going to be 0.45. What about E? What is the velocity and momentum of the block at t equals 2 milliseconds? 2 milliseconds. It only does this part. So let's find the momentum there. That's going to be equal to this part. So it's P initial. Its initial is going to be equal to 0 Newton seconds, and its P final is going to be equal to its initial plus the change in momentum at t equals 2 milliseconds. Well, let's go ahead and find this. This change in momentum at t equals 2 milliseconds is going to be equal to 0.0015 Newton seconds. So this is going to be 0 plus 0.015 Newton seconds. And that's going to be equal to the final.
So its change in momentum, its momentum in this case is going to still be equal to its mass, which is 0.030 kilograms, times its velocity final. So its velocity final is going to be equal to 0.05 meters per second. All right, cool. Next part. Oh my gosh, I'm so tired of work. So tired of work. All right, question number 5. While being thrown, a net force of 132 newtons acts on a baseball mass of 140 grams for a period of 4.5 times 10 to the negative 2 seconds. What is the magnitude of the change in momentum of the ball? What is the magnitude of the change in momentum of the ball? The change in momentum, remember, change in momentum is going to be equal to impulse, which is going to be equal to force times change in time, which recall is also equal to mass times change in velocity. So let's see. What's the magnitude of change in momentum? So we have a net force of 132 newtons for a period of 4.5 seconds. So we have the force and the time that it's being applied. 132 newtons times 4.2 e negative 2 seconds, which is going to be equal to 5.544 Newton seconds. That's going to be the amplitude of the what is the word? Of the change in momentum. In other words, impulse. If the initial speed of the baseball was 0 meters per second, what is the speed? What will its speed be after it has left the pitcher's hand? Okay, so this impulse was applied on the baseball, and the baseball was initially 0 meters per second. It's 0 meters per second, so we have this v is going to be equal to 0 meters per second. And then after applying this impulse, it will, so it's pi, and then after applying this impulse, its velocity is going to be equal to something else. So it's pi is going to be equal to 0 times its mass, which is going to be equal to 0.14 kg, and p final is going to be equal to P initial plus the impulse, the change in momentum, which is going to be 0 plus 5.544 Newton seconds. And this is going to be equal to, the definition of momentum. Momentum, remember, is going to be equal to mass times velocity. So the mass of the ball is going to be equal to 0.14 kg, and then its velocity is going to be equal to this. Cool. So if we solve for velocity, we get that the velocity of the ball is going to be 39.6 meters per second. Okay, cool. Okay,
Lastly, when the batter hits the ball, a net force of 1,320 newtons, opposite to the direction of the ball's initial motion, acts on the ball for 9.0 times 10 to the negative 3 seconds during the hit. What is the final velocity of the ball? Okay, so this one is going to be, this is after the ball has accelerated up to this point, right? This now has a velocity of 39.6 meters per second. And then its initial is going to be equal to that. It's going to be equal to its mass times its velocity. And then, so its final is going to be equal to its mass, its initial. So its initial momentum plus the change in momentum, which is going to be equal to some force times some change in time. So we have the change in time, which is 9 times 10 to the negative third seconds. And then its force, which is going to be 1,320 newtons. Opposites to the direction of the ball's initial motion. Remember, force is going to be a vector in this case, so it has a direction, so it's going to be negative. So with this, what we get is 0 times 9e negative 3 negative 1,188 Newton seconds. This is going to be its change in momentum. So its initial momentum is going to be its mass 0.014 times its velocity, which is 39.6, which is going to be equal to 5.544 Newton seconds. So its final momentum is going to be its initial momentum plus its change in momentum. So its initial momentum is 5.544 Newton seconds. Its change in momentum is going to be this right here. So its final momentum is going to be equal to negative 6.336 Newton seconds. And this, remember, change in momentum, or momentum in general, is going to be equal to a mass times velocity. So this negative 6.336 is going to be equal to the mass of the ball, 0.14 kilograms, times its velocity. So now we just solve for velocity. Its velocity final is going to be equal to negative 45.28 meters per second. Cool. Okay, for the sake of time, I'm going to skip question 6 on the SI review. But if you would like to solve it, I have attached a key with the correct answers. Maybe I will explain the process for that one later. But I wanted to go over a question with both inelastic and elastic collision. This one will have one or the other. I will let you figure out which one. Train cars are coupled together by being bumped into one another. Suppose two loaded train cars are moving towards one another, the first having a mass of 160,000 and a velocity of 0.3 meters per second, and the second having a mass of 115,000 kilograms and a velocity of negative 0.12 meters per second.
what is their final velocity in meters per second. So I want you to try to determine whether this is an inelastic or an elastic collision. Okay, so this right here is going to be an inelastic collision.
Because the train cars, when they're bumped into each other, they couple together.
Remember, when in an inelastic collision, two things are separate. They move towards each other, and when they collide, or they could be going opposite directions, it doesn't really matter as long as they end up colliding somehow. Once they collide, what's going to happen is they're going this way together, or the other way together, maybe even this way together.
But the point is, they're going together.
That is an inelastic collision. Try to recall something that is special about. Try to recall properties about an inelastic collision that we can apply here. I'm talking specifically momentum and energy. So for momentum is conserved. So change in momentum is going to be 0. Now what about kinetic energy? Kinetic energy, the change in kinetic energy is not going to be 0. It's not going to be 0 in this case. They lose some energy when they couple, when they collide each other, when they bump into each other, they stick to each other. They lose some energy because of that.
So with that, we know change in momentum is going to be equal to 0 because it's inelastic. Okay, so let's see what happens here. So since change in momentum is going to be 0, P initial is going to be equal to P final. So let's see what we can do here. Let's find the momentum of the system initially. So the initial momentum is going to be, the first car is 160,000 times its velocity, which is 0.3 meters per second, plus its final velocity, it's 150,000 kilograms, times its velocity, which is negative 0.12 meters per second. This is going to be its initial. So what about its final? Well, its final, if they're coupled together, is going to be m1 plus m2, and they're traveling at this velocity, whatever this final velocity is going to be. You could either write it like that, or you can, if you want to, you could write it m1 plus m2. These are both equivalent. Okay, so let's go ahead and solve for velocity final. If pi is, if the initial momentum is equal to the final momentum, then we have this. Oh. Is equal to this. Is equal to this.
Okay, cool. So we know this already. So we only have one unknown, which is velocity final.
So we can solve from here.
So let's go ahead and calculate our values. This is going to boil down to 48,000 Newton seconds minus, I'm doing minus because I already know the sign, minus 13,800 Newton seconds. Does this make sense? We have a second train car which is traveling at a velocity of this much. So remember, momentum, unlike energy, is a vector. So this one's going this way, so it's going to have a positive value, or if we define it this way, it's positive. And if we have this one moving this way, this one's going to have a negative value. So that's the reason why it is negative. You can also see that its velocity, which is negative, times its mass, which is positive, is going to be negative. So in that way, you can see that it is also going to be negative. This is going to be equal to 275,000 kilograms velocity final. So the difference between this and this is going to be equal to 3,500 Newton seconds divided by 275,000 is equal to velocity final.